Good afternoon and welcome to this SECLI-FIRM webinar titled Sharing Climate Services Experiences between the EU SECLI-FIRM project and in the USA. My name is Leslie Penny and I'm the SECLI-FIRM project manager. This afternoon we have a short introduction to SECLI-FIRM followed by 3 presentations. The first is from Katie Powienczyk from the Met Office, UK, with a presentation on promoting the integration of seasonal climate forecasts in the water sector to help mitigate stress events in the supply-demand balance. The second is by Carlos F. Gaitan from Benchmark Labs, USA, complementing the US public sector's climate services and the role of machine learning and cloud computing. And thirdly, Jan Dutton from Prescient Weather USA is presenting S2S forecasts for energy markets. Before we start, we have some housekeeping and we'd like to record the webinar so we can make it available for promotion afterwards. Also, if you have any questions, please type them into the chat and specify which presenter they are for. Lucy, the comms officer, will collate these and they'll be answered right at the very end of all 3 presentations. And lastly, when you leave the webinar, there'll be a very short survey, just 3 quick questions, and this feedback is really useful, so please complete it if you can. So I'll now start with a short introduction to SECLI-FIRM. So SECLI-FIRM is an EU H2020 project titled The Added Value of Seasonal Climate Forecasting for Integrated Risk Assessment, and it's promoting the integration of seasonal climate forecasts into energy and water applications. And it focuses around 9 case studies where we assess the value of using a seasonal forecast. And you can see here on this slide we have 9 case studies, and they differ for geographical area and for different climate events. And for each case study, there's a co-designer or end user. So I'll just give you a minute to look at this slide and look at the details for each different case study. So a value assessment is performed for each case study, showing how the decision at the end differs. And we have 2 groups. We have the control group A, using climatology information, and then the test group B, which uses climatology information plus the climate forecasts. So as you move along, each group will make a decision and then the value added is assessed and calculated. And again, for each case study, we develop a decision tree. Now, these can take a long time and they're quite complex because for each different case study is a different decision process. And you can see for this one here, there's the decision of booking boats and scheduling teams and scheduling work. So understanding the decision tree process helps to assess the value. And this shows a decision tree for an offshore situation. So under column A, we have the actual decision tree, and then column B, we have the seasonal climate information, and they can be mapped. For SECLI-FIRM, we're developing different ways to deliver climate services. So from the simple data delivery, which was shown on the previous slide, to more sophisticated online visual tools. And this particular slide is showing the situation for energy traders visualized in a tool. And for each case study, we have case study flyers, which are 4-page flyers, and they contain all the information and details about the case study, and they're all available on our website with the web address there. And along with the flyers, we have details of all events, so webinars, workshops. We have the public reports that we deliver to the EU for the project, and full contact details if you'd like further information or to contact the project. So thank you for listening to the introduction, and now I'll hand over to Katie and make you presenter, Katie, for your presentation.
Brilliant, thank you, Leslie. Can you hear me?
Yes, perfect.
Brilliant, thank you very much. Yeah, so my name's Katie Hobienchik. I'm a senior scientific consultant and I work at the Met Office, and my role is primarily developing weather and climate services for various industries, including the water industry and the energy sector. So today I wanted to talk to you about the work that I've been doing for SECLI-FIRM, which is for case study 9, which is about integrating seasonal forecasting data to improve the decision-making process for demand and supply balance decisions that are made within the water industry. So we've been working in partnership for this project with Thames Water, which are based around the London area of the UK. And I'm just going to step through the approach that we've followed in this project and show you some of the outputs that we've developed by working in partnership. So it's been a very iterative process. User engagement has been absolutely key to this process because, as Leslie said, what we wanted to be able to do at the end of this project is quantify the benefits of integrating this new climate data into the decision process. So in order to do this, we had to, first of all, map out the decision process of the water sector and identify opportunities where we could integrate seasonal forecast data into the decision process. And we really needed to define what the user requirements were. The next step for us as the co-developers was to go away and look at the science and work out how we could tailor the science or the seasonal forecast data for the particular application that we were developing with the water sector. We've then worked very closely with Thames Water to co-develop and deliver a trial forecast service over the past 6 months. But throughout this process, we've been constantly reviewing the service and improving it and looking where there are gaps that we could further improve or provide more support. So I'm just going to step through this process that we've followed. So first of all, in terms of initial engagement that we had with the water sector, we ran a series of workshops, and the idea behind these workshops was to capture the decision process and really understand how the supply-demand balance is managed in more detail, because this was going to provide the baseline from which objectives improvements could be quantified. From these workshops, which we ran with numerous water companies across the UK, we were able to identify key case studies where extreme fluctuations in demand put a lot of stress on the water systems. So one of them was the summer of June, July 2017, and this is when there was some really hot weather, so you get really large spikes in water demand or water consumption, essentially, because people are using more water to water their gardens or to mainly need to water their gardens or paddling pools or fill up their swimming pools. And another case study that we identified was in March 2018, the UK experienced some really cold weather, which has been dubbed the beast from the east. And what this caused is lots of pipes to freeze, and when they thawed, we had lots of burst pipes, which again caused a lot of stress on the supply-demand system because there was a large spike in water demand. So we've been working with water companies across the UK, but our predominant partners are Thames Water and United Utilities, which you can see in the map here. I've highlighted on the map on the UK. So it's been good to work with water companies from different areas of the UK as well, because we can test the skill in the forecast service that we've developed across the UK. So this is an example of a decision tree that we've developed in partnership with Thames Water, really to outline the decision process that goes into planning the water production process to ensure that the amount of water that produced every day is going to meet demand. And there's essentially two opportunities we highlighted to help identified where climate services could help improve the decision process at longer lead times. And one is whether there's an opportunity, potentially, if there's going to be lower demand scenarios in the upcoming weeks, there might be an opportunity to carry out extra maintenance on the treatment works, which is beneficial as the water treatment work should then work more efficiently. And another opportunity is to potentially identify peak demand periods that might be coming up with high risk, because that enables water companies to act earlier if they know these risk periods are coming up. So, for example, they can increase their resource so that they have more people to tackle the problem when it occurs, and they can also send out communication before to try and reduce the impact of peak demand periods on the system. So these are the two key decisions that were identified in the seasonal time frame. Just going back to this slide, what the water companies at the moment have to predict demand is they use a relationship between weather and demand to forecast demand out to 10 to 12 days ahead. And what we wanted to do is extend this forecast predominantly up to 1 month ahead. So this is where we went away and we looked at tailoring the science for the application. So the current demand forecast uses the weather parameters as inputs to the forecast, but we know at longer lead times, broad scale circulation patterns are much easier to predict. So what we've looked at in this project is the relationship between broad scale circulation patterns, which you can see on the right-hand side of this slide, and demand. So what you can see in this slide is if you're in weather pattern 1 in the winter, there's a much higher risk of peak demands happening compared to if you're in weather pattern 2. And this makes sense because weather pattern 1, you get very cold weather coming across the UK, so you get increased leakage and burst pipes, whereas weather pattern 2 tends to mean that you have warmer, wetter weather, which reduces the demand in the winter. So once we were able to establish this relationship between weather patterns and demand using historic weather patterns and historic demand data, we were then able to combine the forecast of the weather patterns with the risk of demand exceeding a critical threshold in that particular weather pattern. So that's the process that we've followed to essentially extend the demand forecast out past 10 days ahead. And once we were able to extend the demand forecast, we then worked closely with Thames Water to optimize the forecast of the format, optimize the format of the forecast. So this is an example of water demand during that beast from the east period. So what you can see here is this is daily water demand in January and February. And as you can see, it's relatively flat, around 100 megalitres per day. And what we can see here at the end of March is a really big spike in water demand. And that spike was caused by really cold weather, resulting in lots of burst pipes and leakage. And so this is an example of the forecast service that we've developed to help Thames Water identify these risk periods coming up in the future. So this is the example of what the forecast would have looked like on the 8th of February. So you can see we're essentially saying it's a low risk of high demand, or this is the probability of demand exceeding that 100 megalitre threshold here. So the probability of exceeding it was relatively low compared to climatology at the beginning of February, based on our forecast, which, as you can see, that's true because it hasn't exceeded it very many times. And as we extended out our forecast into the beast from the east period, you can see it becomes a red status because we think there's a much higher risk based on the forecast of the weather patterns that demand are going to exceed critical thresholds. So that's one way of presenting the data. There's lots of different ways of presenting probabilistic forecast information, and we've been working alongside Thames Water to optimize this. This is another example, and again, it's showing the same information, but we also wanted to capture on this the probability of climatology as well. So what you can see in this graph is the risk of demand exceeding critical thresholds that are important to Thames Water. And as you can see, normally during February and March, the risk of critical thresholds being exceeded generally decreases with time. And that's because the weather should be warming up. And so the risk of getting high leakage or burst events should be decreasing. But what you can see here is in the shaded area is the probability of based on the forecast of the demand exceeding this threshold. So you can see during this period here, the risk was much lower than climatology. So this was like a green period for Thames Water, whereas this is a much higher risk period. So finally, as I said, this is quite a circular process, and we wanted to continuously review and improve the service. So this is just an example of some of the iterative steps we followed in developing the visualization tool with Thames Water. So it started out as a very deterministic forecast service, only extending out to 10 days ahead. We then looked at adding ensemble forecasts into the forecast, but it was really important, as that's really important, especially with seasonal forecasts. But we started off by looking at percentiles, but this created a kind of a very wide uncertainty band, which was difficult to make a decision with. So what we then looked at doing is turning this information into a threshold approach, so that a binary, just even though we were providing probabilistic information, we could turn it into a binary decision. And finally, we've developed that RAG status that I just showed you before, which is able to turn the probabilistic information into a warning system, showing red when there were risks, extreme risks of high demand. So what I just wanted to show you here was ongoing monitoring of the trial service that we set up in November for this seasonal forecast. So recently, the UK has actually experienced very similar weather to the weather that we experienced in March 2018. Probably nothing compared to the weather's probably nothing compared to some of the weather you'd expect in the USA. So it's not as extreme at all, but we have had some cold weather for this time of year, and there's been snow in quite a lot of parts of the UK. So I just wanted to show how our trial service was able to capture the risk of this happening. So this was our forecast on the so the snow and the cold weather which carries a risk of high demand has happened around the 8th of February. This was our forecast on the 16th of January, so nearly 3 weeks before the weather has happened. And as you can see, it wasn't highlighting a red event, but it was highlighting at that point an amber event. So it was suggesting that you should be wary of that period that was coming up. And then as you can see, as we got closer to the event, we then moved into that red status. And this extra warning allowed Thames Water to prepare for this event. So they were able to send out a lot of communications in advance to try and ensure that office blocks were checking their pipes and making sure that if they had burst that they could fix them quickly, and they increased their resource over this period in advance so that they could fix more of any pipes that caused them any issues. So just in terms of our next steps, really the next step now is to evaluate the economic benefits of the service that we've developed. So we're going to use the decision tree to help quantify the benefits as we understand what the decision process was before we integrated climate change data into it, and now we can understand what it looks like with the climate data. We've also attached some kind of costs that we think are associated with the decision process, so that will help us evaluate the benefit of making a decision over with and without the climate forecast data. We're also doing some more communication of the service to the wider water sector and letting them know about this service that we've developed. And we also want to work alongside the water companies to make sure that this service becomes fully integrated into their operational process and is available to any water company across the UK. Thank you for your time, and I'll answer any questions after.
Great, thank you, Katie. If you'd like to make me presenter again, and then I can hand over to Carlos.
Great, thank you. I think I've done that.
Lovely, thank you. Okay, Carlos, I'll hand over to you.
You want to show my window? Hi, how are you? Hey, good morning. Afternoon. Thanks for attending this webinar. It's my pleasure to talk about the role of machine learning and cloud computing services on complementing the US public sector services. For those of you that are not aware, in the United States, thanks to freedom of information, most stakeholders can access climate data, weather data, observational data that had been funded thanks to government funds or public support one way or the other. So here the problem is not to get the data, is necessarily to find the data. And once you find it, if the question is, do you know how to access it? Do you know the format that is it? Can you operate them in a way that it will enable data science? So from the perspective of Benchmark Labs, we're a startup working on the agricultural sector, focusing on point-specific, asset-specific forecast and information. This experience is very rewarding, as you can see a transition between a totally public model and a hybrid model, and we're going to talk more about it. So next slide, please.
Lucy, I think I need to hand presentation to you so that you can show in presentation mode.
Can you see my slide now? The
we
next
can
slide.
See your slide, but not in presentation mode.
Okay, let's. And I'll stop.
Okay. What I'll do, I'll hand to Lucy, and she can show your slides in presentation mode.
Let's try now in Perfect. Let's go to a second slide. Yeah, perfect. Thank you. Okay, so yeah, we were introducing Benchmark Labs, and we basically integrate IoT data coming from in-field sensors with publicly available climate information. We started by integrating it with information from the global forecasting system from NOAA that was in a very obscure server, but we found it. And then our stakeholders also mentioned that they had needs, as we heard from the previous presenter, to get seasonal information, which is actionable once you are thinking about the labor scheduling, harvest forecasting, and other farm management activities that happen beyond the traditional 10 to 15 days period that you can get from weather models. So next slide, please. So our approach manages to reduce the error in comparison with publicly available data, gridded data, by doing this statistical downscaling using machine learning techniques by around 35% in case of temperature, precipitation. You have like similar ranges of improvement, and it's that's striking once you are looking at extreme events and in-field behavior, because of the microclimates at different farms are so different than information that you usually get from the nearest weather station or from the gridded model. So next slide, please. So what's the problem? The problem is, where is the data? So now let's start clicking here. So next click. You can find data in portals like the GFDL data portal, that is a laboratory from the Department of Commerce. If you know where to find it, it's there. Next click, please. You could try also to check the North American multimodal ensemble models that are at the IRI. And again, this is the interface that you will face. Another alternative is, next click, it's data from NASA. You can go to the NASA webpage for the GOES Mira S2S model and download it directly. Or you can, next click, go directly to the NMME page where you can find anomalies, seasonal forecast, 1 month anomalies, different timescales, but often these pages will lead you to JPEG files that are not necessarily gridded or you don't have metadata, and you will have to find where are actually the netcdf files if you want to do data science or calculations that will have like some kind of data that you can quantify. Next click, please. Alternatively, you can go to NCEP, and it's an interface where it shows basically all the available models that they have. In this case, I'm showing all the possible runs that we have available for the GFS model at 1/4 degree, 1/2 degree, 1 degree, different use cases, spatial domains, and so on. So as you see, the problem is where you find the data that it's appropriate for your tasks. Next slide. So what's the solution? So recently, probably 5 years ago, the US government signed a memorandum of understanding with leading cloud computing providers. Think about, in this case, this is Amazon Web Services. Next click, please. Microsoft Azure has an initiative of AI for Earth. And next click. Google has an Earth Engine data catalog. The idea is that Microsoft, Google, and Amazon will increase the availability of publicly available data by linking their storage systems that are actually in the best interest of these companies and these providers to increase the usage of that. They charge individual users and academic users for storage or cloud computing and enable new data science problems. So, for example, Microsoft has grants on AI for Earth for companies that are interested in using these publicly available data sets for science applications that relate with the Earth environment. Similarly, these are some of the use cases that they also host European data, Australian data, Canadian data for crops, even biomedical data that you can find in open repositories. So this was considered as a win-win situation where the data became more accessible, and these leading cloud computing providers got access to new data sets that will allow them to monetize and get new customers. Next slide, please. Perfect. So let's now talk go back to our seasonal forecasting focus, and I will showcase 2 use cases in the following slides. One is a case for agriculture, where we are going to look at the potential of using seasonal information from the NMME to calculate cumulative growing degree days. So what's the problem statement? Basically is in agriculture, depending on which crop you are interested in, you can look at the cumulative number of growing degree days that are needed from the moment that you plant to harvest or to reach different phenological stages. Growing degree days, usually it's a very simple formula, depend on a threshold that is specific to the crop and maximum and minimum temperature. So in this approach, we're going to use data from the NMME, weather data, to link it to a specific location and see the evolution during the harvest season. And the constraints are we're going to show you the cumulative growing degree days for wine grapes. So let's go to the next slide, please. In this slide, what you can see is in blue, you have a climatological line, which is based on climatology where you will expect to reach the growing degree days. On the red line on the top, around like 1,750, that's the number of degree days needed to reach maturity or to harvest these specific grapes. And we compared this approach with an analog method, the most similar year on record, which is traditional. And the difference here was for this specific case, we took information from the seasonal models of the NMME, the multi-model ensemble. And during the season, in this case, the black line at the bottom shows that we are in mid-May. We did the forecasting going forward and say, okay, based on the accumulations that you could expect from the NMME forecasts, where would you get the harvest date where you reach 1,750 units? NMME at that point was predicting a late harvest around October, mid-October, while the climatology and the similar year on record was basically saying that it's going to be mid-August. So it's a huge range. Traditionally, the farmers will go for the mid-August range, as is like what they are used to use. But new tools like the NMME give an opportunity to see if there is actually a different uncertainty on this. So let's click on the next slide, please. So after the season progressed and we reach September, the black line is the observations. You see that actually the NMME forecast, and we were updating them every month as we received new data from the NMME, were closer to the actual date that was first week of October, second week of October, while the climatology was off by more than 1 month. Of course, once you add the climatology, in mid-September, your ranges get reduced. But here, what you show is if you are going to make decisions in May, there is potential information that can be obtained from the NMME that can help you to improve your farm operations. So next slide. The next use case is a proposal that we recently started with NASA. The rationale of this is, do COVID-19 lockdowns drive the decline of active forest fires, increasing summer wildfire risk, basically? So what we have here is basically as a question. We have data from the MIRA GEOS S2S model from NASA. NASA provided us with daily data for the seasonal model, which is hard to get. Let's say if you're going to the NMME, you will have to maybe access that kind of data from the IRI here in the United States, as the NMME webpage usually only provides a monthly data. So NASA provided us with daily data, and our idea was to calculate the KBDI index, that is a drought forecasting index, that could be used as a proxy for forest fires. We will need we needed precipitation data and maximum temperature data, and the idea is that then we will map historical fires, historical fire activity, and see if there is some similarities in drought index areas that had a forest fire activity at the seasonal level. We ran this in a Saturn cloud server, 2 cores, 16 gigabytes of RAM, 40 gigabytes on disk. This was a high resolution run at around 6 kilometer spatial resolution over the United States. We managed to run this on 2 core 64 workers in a DAS cluster in AWS, just for the technical details. Next slide, please. And here what you see on the left, it's based on the model run of July, two different time steps, basically. The forest danger index based on the MIRA S2S data. First on September 2020 here on the left, and December 2020 on the right. Now that it's now February of 2021, we can say retrospectively that these conditions actually mapped very similar to what actually happened. Basically, the western part of the United States was in a very severe forest fire danger area. In many ways, we have like forest fires from Northern California up to the south where I am now, up to October of 2020, and the conditions then normalized on December. So what is next for this project? Of course, we're going to look at more uncertainty coming from different models. In collaboration with the Forest Service, we are going to see how this map into 2021 and look at the possibility of using operational models that will assimilate and will create this forecast for the public. Next slide, please. Next steps in terms of like in the relationships of public-private partnership relationships is there is hope here in the States. NOAA recently announced that the Unified Forecasting System subseasonal to seasonal prototype it's available in AWS. That means that you could link it much more effectively instead of trying to find and dig deeper where the information is, in which format is. In this case, for Amazon, you access one of the resources that are there listed in red on the right hand side of the screen. That's basically the URL where you can connect and point the data to perform operations. The data is structured. You can use operations in time and space, use Amazon services like Athena to query it. So there is hope that these data are going to be more widely accessible, especially the seasonal to subseasonal information. And by talking with Google, Microsoft, and Amazon from the perspective of a small company or even a bigger company, what they are looking is for use cases. So they told me, if you need a specific data, please let us know and we can make the case. So they actually are hosting, for example, the ECMWF ERA 5 data to GHCN Historical Climatology Network of stations globally. So there is hope that in the future they will host more seasonal information coming from the IRI or other modeling centers. So thank you. Next slide. I just want to thank our sponsors and NASA for the access to the data and the National Science Foundation. So thank you very much. I will ask the audience if there are any specific questions, and I will gladly answer them after the next presenter. Thank you.
Lovely. Thank you, Carlos. So Jan, you are presenter now for your presentation.
Great. Oops. All right, everyone can see the presentation?
Yes, perfect.
Okay, great. So first off, just I'd like to thank the SECLI-FIRM team for giving us the opportunity to present. I'll mention it in a little bit, but you know, the European Union has a very well organized climate risk research program that, to be honest, I kind of monitor quite closely. So given the organization and some of the work coming from Europe, it's an honor to be able to present and talk about an American-born climate service. So by way of introduction, the company here is Prescient Weather Limited, and so we're a US company that was founded in 2009, and we are trying to focus more on climate-related applications. So we have both Crop Profit, which is a corn, soybean, and winter wheat yield forecasting system. And so interestingly enough, the variation in crop production from year to year for quite a wide range of crops is primarily due to the weather conditions that occur during the crop season. And then the other is the World Climate Service, which I will talk about today. And we're going to focus on talking about seasonal and sub-seasonal forecasting. Oops. So just to make sure we're all on the right time scale, within sort of weather and climate information, there's a wide range of potential applications and sources of information. There's everything from nowcasting, which is a forecast of what's going to happen in the next couple of minutes to the next couple of hours. Weather forecasting spans generally a few days to up to 10 to 14 days. And then sub-seasonal is in this interesting time frame where the information of the initial conditions is either gone or dropping off quickly, and information associated with boundary conditions is picking up really rapidly in terms of creating forecast skill. And then seasonal forecasts is exactly what it says, which is forecasts in, say, months to seasons in advance. And then you get into sort of climate risk discussions with regards to climate change, and you're talking about projections. That is generally decades in advance. So within the World Climate Service, we're trying to focus on the sub-seasonal and seasonal forecasting capabilities. And as I mentioned, or as I had on the first slide, the World Climate Service has actually been in existence for about 15 years. So I guess I like to say that we were providing a climate service before climate service was a term. And so the World Climate Service provides a single source of objective seasonal to sub-seasonal forecasts and analysis information. And what we're trying to do is enable forecasting with a probabilistic and a risk assessment focus. And so Carlos actually in the presentation before gave a great example of all the different sources of places you can go to get information. What we're trying to do is gather all that information into one single web source. We're trying to add value to it. And then we're trying to enable customers to be able to make probabilistic assessments and risk assessments of the likelihood that weather or climate conditions may disrupt their operations, or there may be an opportunity. So our primary customers are in fact commodity trading desks that generally employ a meteorologist, and those commodity trading desks are trading electric power, generally natural gas, as well as agriculture commodities. So what's interesting about the World Climate Service, from my perspective, is Katie showed a great example of trying to do somewhat of an automated forecast capability to alert an end user to a risk. And what we're trying to do is we're trying to provide objective information to allow a meteorologist to prepare subjective forecasts to be able to communicate with their stakeholders on the trade floor. So in terms of providing objective information, there's really there's 3 or 4 types of information that we provide depending on how you look at it. One is calibrated ensemble forecasts, and I'll talk about this in just a little bit more in a moment. The other is analog analysis and analog forecasts. So in the case of analog forecasting, the methodology is primarily using the reanalysis data to find times in the past that are very similar to today. And if you can find those time periods, you can use what progressed from, you can use the conditions that progressed from what happened in the past as an indication of what may happen in the future. We also provide statistical forecasts, and I have an example of the value of statistical forecast shortly. And then we're also tracking the climate indices. We're enabling monitoring of the climate indices, and then we are providing forecasts of the climate indices as well. And so the idea then is that we're providing all of this information, and it allows end users to intercompare all of the information to try to assess the likelihood of a future outcome. So just to mention for calibrated forecasts, today in an operational sense, the World Climate Service provides calibrated sub-seasonal forecasts from the CFS, from NOAA's CFS and the ECMWF Extended Ensemble. And then we have a proprietary multi-model ensemble. We are about to release a calibrated subseasonal forecast for the global ensemble forecast system, so NOAA's new model. And then we're very close to releasing as well subseasonal forecast for the Japan Meteorological Agency Model 1 run as well. And so one of the challenges you run into, for instance, in doing a multi-model ensemble, is that these models are not always released on the same cycles or even on the same days. And so there's a bit of a stitch game that you have to play to try to do multi-model ensembles. For seasonal forecasts, we're using the climate forecast system and ECMWF. And then as an example of leveraging some European content, we also have calibrated versions of the model runs made available by the Copernicus climate system. So we have each of those climate models as well as a multi-model ensemble as well. And so what our customers are doing is they're comparing the different sources of information to see if they can extract or analyze towards the same signal. And if they can find that, then it gives them a better confidence in the forecast that they are communicating to their stakeholders. So one of the things that we believe in providing this climate service is that multiple sources of information add value. So I mentioned that we have both dynamical models and we have statistical models. And so we've done some research in the reforecast space. And what we find as an example is when the dynamical model and the statistical model have broadly the same pattern, that the dynamical model is on average more accurate. And so as the bar chart on the left is a skill comparison of a May, June, July forecast, that we see that the skill score on average is higher when the pattern between the two forecasts is agree, and the skill score of the multi-model ensemble is lower when the two models disagree. And so I'll just say on the right-hand side is a comparison of the patterns depicted by the dynamical model and the statistical model. And this is a good example of a pattern that agrees, right? So there's in the upper dynamical model is a probability forecast where the blue areas show increased probabilities of below normal temperatures, and whereas the statistical model is it's a pure anomaly forecast, but it shows, right, so colder than normal conditions are likely in the Canadian prairies, and then in the southeastern United States there's a bit of a warm signal as well. So this is an example where the patterns are similar. And as a meteorologist communicating risk to stakeholders, you might be willing to say that the dynamical model is likely, you might have more confidence in the dynamical model because these two patterns agree. So the idea is to take what I call semi-independent sources of information and try to compare the signals to see if there's similarity. So it's kind of like an ensemble of methodologies rather than just an ensemble from a single model. So I've mentioned calibration a few times. Calibration is an important step as well. So calibration is a two-step process in which we use the model reforecast data to correct for model biases and to adjust the ensemble variances to increase reliability. So the idea is that one of the models, whether it's CFS or the GEFS or the ECMWF, it is the modeler's best attempt at modeling the real world, but there's always going to be errors. So we use the average climatologies in the reforecast to compare two products such as the ECMWF reanalysis, and we can remove the error, the average error that occurs for a different season or a month or a week over a long period of time. And then in general, these ensemble forecasts, they tend to under forecast the variance or the variability or the uncertainty of the forecast. And so we run a process to try to adjust the ensemble variance to increase the reliability of the forecast. And so in this case, for reliability, what I mean is that if you forecast an event such as above normal temperatures with a specific probability, so let's say 70%, the idea is that that forecast or that event, if I forecast above normal temperatures at a 70% probability, that event should occur 70% of the time that it's forecast. And so calibration helps to achieve that goal of creating a reliable forecast. And so the idea then, again, so here's a week 3 forecast from our multi-model forecast showing higher probabilities of colder than normal temperatures. So I show this as an example of the probability forecasts over a relatively large geographic domain. And so we can use a long history of these types of forecasts to estimate, when we forecast colder than normal temperatures with 50 to 60 or 60 to 70% chance, how often does it happen? And so we graph this information using a reliability diagram. So the x-axis here is the forecast probability, and then the y-axis is the observed frequency. So it's the forecast of the above normal or below normal conditions, and then how often does that occur in the observations. So the ideal solution is to fall on the 1-to-1 line. If you forecast something 70% of the time, it should occur 70% of the time. And what we see then is for the GEFS model, and so NOAA's GEFS model, the uncalibrated version tends to overforecast the probabilities. But once you calibrate the forecast, then you have a much better sense of the probability of being correct. And so the process is such that calibration tends to improve the reliability of the forecast. So calibration also then allows the end user to understand or to have confidence that the probability is directly related to the skill of the forecast. So what I'm showing here then is two forecasts. One is, this is December, January, and February, week 3 forecast for Europe, which is say averaged over Europe for 2-meter temperatures. And the x-axis is the probability, it's, as it says, the probability of at least. So the 35 is that all probability forecasts that were 35% or greater for warmer than normal or colder than normal. And then as you go out the x-axis, you're narrowing the scale of the probabilities. So by the time you're at 55%, we are looking at the skill of the forecasts of all forecasts that were made that were 55% or greater. That the y-axis then is the tercile fraction correct, which is a skill score that we use. And so the idea is we're forecasting above normal and below normal conditions. And if we forecast above normal temperatures with 70% chance, and 3 weeks later, it turns out that a particular grid cell was in fact warmer than normal, we say that that forecast was correct. So the tercile fraction correct is the number of forecasts we made that were correct. And what we see then is that calibration allows us to understand that as the probability gets higher, the skill of the forecast increases as well. And so then I'm also then showing that the CFS ECMWF GEFS is a 3-model, multi-model ensemble. And again, what we see is that multi-model ensembles add skill to the overall forecast. Now, at around 60% there, we see that the skill reverses. And my guess is that that is probably a statistical aberration. And the reason I say that is one of the things that happens is as you go into higher probabilities, the frequency that the forecast is made decreases substantially, right? So we know that the ensembles, the variance of the ensemble tends to increase with lead time. And so as we get into the week 3, the ensembles are already quite distributed. And for a forecast of 60 or 65% to happen, you'd have to have remarkable agreement between the models or between the ensemble members. And so that doesn't happen very often. And so my guess is that the change in the rank there is probably due to just a sample size rather than actual change in skill. So then being able to relate the probability to the likelihood that that forecast is going to be correct creates an interesting opportunity, which we call forecasts of opportunity. So again, using the dynamical models, you can take periods or forecasts far into the future when the probabilities are quite high, and in effect, use that as an understanding of the risk of a particular scenario. So it turns out very early in this year, it was quite cold in China and Japan. And there was, because of the cold conditions, there was a much greater than normal consumption of natural gas, and the liquid natural gas industry wanted to ship a lot of product to Asia, but they were unable to because ships were not available to do it. And so the cold snap created a substantial price in natural gas in Asia. So when I saw this headline in the Wall Street Journal, of course, I went to the World Climate Service and I looked at our forecast. And what I'm showing here then on the left-hand side is our week 3 forecast. where we see some signals of colder than normal conditions, of greater than normal probabilities of colder than normal conditions. But by the week 3 forecast, a week later, we see that this cold forecast is pretty well locked in. And we even see, I believe that is 70 to 80% chance of below normal temperatures in some places. And then on the right-hand side is what actually happened. And so I always find in this case, when this happens, this is quite remarkable because we see the pattern is quite similar to that week 3 forecast. And so this is a chance where there certainly was a trading opportunity if you were looking at the week 3 forecast in the World Climate Service. And then you could do the risk analysis to understand that there was a shortage of LNG ships and the price in Asia was likely to increase. But the key then is that the probabilities enable the evaluation of risk. So I mentioned that we provide objective information to enable meteorologists to create subjective forecasts. And so within the World Climate Service, we do a subjective seasonal forecast that is updated on a monthly basis. And then actually our partner DTN creates a subjective subseasonal forecast that targets Europe. So both subseasonal and seasonal subjective forecasts are created. And so I just give an example here of the seasonal forecast from May of 2018 for the summer of 2018, where warm conditions were forecasted. But the reason I want to set this up is that one of the things that is interesting about the subjective forecast is that we've been making these subjective seasonal forecasts for the entire lifespan of the World Climate Service, right? So as of now, we've made 144 seasonal forecasts, and the forecasts are what we call the fuzzy maps, and we basically do pattern correlations on these fuzzy maps to see how accurate our forecasts were. And so the interesting result of the performance of these forecasts is we see that as the confidence increases, getting the direction correct of the forecast increases as well. So this is very analogous to the graph I showed, that as the probability goes up, which is to say, as the confidence in the forecast increases, the likelihood that the forecast is going to increase, the likelihood that the forecast will be correct increases as well. And so the other interesting point about this is over time, we've added more and more tools, which is to say the objective information, the amount of objective information available to the forecasters creating this forecast has increased as well. And we see that the later forecasts perform better than the earlier forecasts. And so the tool then is a climate service in the sense that it's providing a lot of objective information, but our use case then is to enable meteorologists to create subjective forecasts to inform their users of the likelihood and the risks in the coming weeks and months ahead. And so the conclusions then are that the seasonal and subseasonal forecast performance benefits from multiple sources of objective information. So we're trying to avoid reliance on the dynamical forecast and provide basically as much information as possible about the likelihood of future outcomes. And then a probabilistic analysis enables quantification of risk and the communication of confidence. And then as can be expected, we plan to continue to do research in this direction. But we know that the overall community, the global weather enterprise, is working to make these seasonal and sub-seasonal forecasts increasingly valuable. And that is all I have. Thank you very much.
Thank you, Jan, and thank you to Carlos and Katie as well for those presentations. Lucy's compiling the questions and then we'll show her screen, so then we can address the questions very quickly.
Right.
Can you see my screen okay?
Yes, perfect, Lucy.
Okay, so thank you so much to everyone for their presentations. We are right on time now, so we'll just take one quick question for Katie. Katie, can you see that okay?
Yeah, that's fine. Sorry, my dog might be barking in the background, but yeah, I think the answer to that one really is that we worked very closely with Thames Water to understand at what threshold they started kind of feeling strain on their system. So there's this kind of normal amount of water demand that they normally see every day, and it's when you get peak periods such as hot weather or cold weather that they start to get this stress. So that's how that 100 megalitre was chosen, because it was kind of above the normal kind of operating everyday level, essentially.
Okay, thanks very much, Katie. So I'll just wrap up now and say a big thank you to our UK and US presenters and to all of you who made our EU H2020 SECLI-FIRM hosted webinar part of your Wednesday. We really appreciate you joining us. The webinar recording and copies of the presentations will be shared on our project website. And if you do think of any questions, or we haven't had time to answer something that you really want us to come back to you on, please do email through the website and we'll get on that. You can follow SECLI-FIRM on Twitter and LinkedIn for regular updates. So all that's left for me to say is enjoy the rest of your day or evening, and thank you for joining us. Goodbye.
Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you.
Thank you very much.